Swayam Prabha. Digital India. Educated India.
So here are the transportation problem solution algorithms. So that should be our topic today. And as the title suggests, can you all see the slide? Right. So the transportation problem solution algorithms. So we'll summarize what we have discussed in the transportation problem so far, and thereafter we'll take up a number of problems and try to understand certain very important things. All right. So first of all, the LP formulation of transportation problem these starts with minimize z equal to double sum I equal to 1 to m, j equal to 1 to n, I and j, they are source I and destination j. So there are m number of sources and n number of destinations, and ai is the availability at source I, dj is the demand at destination j, and Cij is the cost of transporting 1 unit of material from source I to destination j. This should be small I. All right. So this is the objective function, because usually our purpose is to minimize the transportation costs, and subject to that it should be within availabilities, and demand must be met. So availabilities less than equal to the availabilities, all the availabilities, and more than equal to the demands. So this is the general formulation of transportation problem. But we have seen that solving this problem is rather difficult, because there will be too many slack, surplus, as well as artificial variables. In order to see matters, what we do, we make an assumption, that is, we take what is known as the balanced transportation problem. How to balance it? By equating total availabilities and total demand. That means sigma ai equal to sigma dj. And when sigma ai becomes equal to sigma dj, only thing that is possible to balance the problem is that sum over the various what you call at a particular destination, at a particular source, the total amount that is transported to different destinations, that should be equal to the availability of that source. And on the demand side, the total amount that is accumulating at a particular demand point, that should be equal to the demand of that particular destination. So for all destinations, and this is for all source, and xij greater than equal to 0. So this is exactly what we are going to have. And here, apparently there are m into n number of unknowns and m plus n number of equality constraints, but we cannot solve all, because these additional constant would reduce one basic variable, and we shall have m plus n minus 1 basic variables. So that we have already discussed in our previous class. So we started this particular transportation problem, but we could not complete. So I said that transportation problem requires an initial solution to begin with. And a quick method to get an initial solution is what is known as the northwest corner rule. So what we do, we make some entry at the northwest corner. So let's say we begin with this corner, which is the northwest corner. So we see that total is 6 this side and total is 11 this side. That means an entry of 6 could be made here. If we enter a 6, then this is crossed, because no more entries are possible. And after this 6 entry, then we see we cannot go down. So we go towards this side, go towards the right side. And there we can see that this side is 10 and this side is 5, because 6 is already gone. So only 5 can be entered. So moment the 5 is entered, this row is then filled. And then the next entry could be in this down. And here then remaining amount is 5 and this side is 13. So F5 entry is made. So like these we have already discussed, and the cells are filled up, and you see that there are m plus n minus 1 entries are made. Sometimes you will not be able to make m plus n minus 1 number of entries. What might happen that moment you enter something, this cell gets satisfied from both sides. Then what to do in that situation, that we shall discuss later. All right. So this is going to be our initial solution. So we have to understand that if these are my basic solutions and these are my non-basic cells, then whether any non-basic cell is going to be coming into the basis. That means if we enter there, then the total transportation cost is going to reduce. Now a quick look in the cell values will see that we are making so much entry, that is 15, in a cell which cost is 41 unit cost. There are cells like 13, then 23, 27, 17, 32. Though values, unit cost values are much lower. That means, there is always going to be profitable if we make some entry in those squares. So quick look actually reveals that. So how to compute the Cij minus Zij? Because the problem is in two dimension, that is, consider the UIs for the sources or the factories and Vjs for the destinations or the warehouses. So for the basic variables, we have UI plus Vj equal to Cij. So this is the UV method, and as you understand that these UIs and Vjs are nothing but the dual variables. Since there are m plus n minus 1 basic variables, we have m plus n unknowns and m plus n minus 1 equations. So solve for UIs and Vjs by considering any one of them as 0. So that is important because you see UI and Vjs are dual variables, and these dual variables are like cost potentials. So, we are writing the Vjs as a negative of the cost potential. So instead of a minus sign, we are getting a plus sign, but nevertheless, they are the dual variables and they represent the cost potentials. So that is why, for the basic variables, Zij is equal to 0. So, the Cij will be the value of the Ui plus Vj. And now for the non-basic variables, the Cij minus Zij would be then Cij minus Ui plus Vj. All right. So since actually, you can interpret it like this, that Ui plus Vj would be equal to Zij. And since this is equal to Zij, then and since Cij minus Zij equal to 0 for the basic variables, therefore we can have Ui plus Vj equal to Cij. Whereas for the non-basic variables, since Ui plus Vj actually represents the cost differential, so that is Zij, that or the loss profit per unit. So for non-basic variables, we can compute Cij minus Zij as Cij minus Ui plus Vj. So this is how to really solve the UV method. We can compute the Cj minus Zj values. So already we discussed it in the previous class. So this is just a repeat. To find the U1, U2, U3 and all the V's, we have to start with one of them as 0. So let us say we take U2 as equal to 0. So if U2 equal to 0, then V2 will be 18 because this is a basic variable and here we have a value of 18. What we shall have is that, these 0 and 18 together should be equal to 18. Now go to this basic variable, there is 14. So 0 plus 14, that should be 14. So since we put U2 equal to 0, we can straightway write V2 equal to 18 and V3 equal to 14. Now, moment we write V3 equal to 14, and this is another basic variable, total is 18. So we can write U3 equal to 4. Moment we can write U3 equal to 4, and we know this is another basic variable. There is a 41 here. So this 4 and 41, so we shall have 37. All right. So like this, we continue. And finally, we see here that we have got an 18 here because this 0 has got this 18. And we have, this is another basic variable. So 16. So U1 should be minus 2. And then after u1 is minus 2, then this one is 21, that is the last basic variable, so v1 should be 23. All right, now after you computed these u's and v's, you could have started with anything else as 0. Like you could have started u1 equal to 0, then v1 would have been 21 and v2 would have been 16. So like this you could have proceeded, and then these 16 and 18, this should have been 2. So like this you could have gone, but always remember that u1 plus v1 would have been constant, is it not? So these would have been 0, these would have been 21. Currently also the total is 21. So all these things are to be checked. So as a cross check, you can just do cross check. So minus 2 and 23, 21, minus 2 and 18, 16, 0 and 18, 18, 0 and 14, 14, 4 and 14, 18, and 4 and 37, 41. So this cross check is also very important. So after you have done this cross check, now go to the non-basic cells to compute Cij minus Zij. So for W4, F1 W4, 13 is the cost. So 13 minus 37 minus of minus 2, that means 15 minus 37, so minus 22. 23 minus 0 minus 37 minus 14. 17 minus 0 minus 23 minus 6. 32 minus 23 minus 4. So that is a plus quantity. The cell is not a preferred cell. And this 27, that is also positive, and this also is positive. So now you can understand that the best possible cell which reduces cost is F1W4. So what we can do, we can make some entry here, and these minus 22, because that is going to reduce cost per unit at 22 per unit. So we have to make some entry here. We can make some entry here. Now the question is how much entry? So this is an important thing. We have to get a closure, because otherwise the transportation solution will not be balanced. Because you see, the total row wise should be 11. So if you increase here, something should be decreased. Now the question is, which one will you decrease? See, you cannot decrease this 6, because if you increase here and you decrease this 6, then which one to increase? You have nothing left to be increased. All right, so you won't get a closure. So you have to get a closure. That means which is can be actually truly speaking in network language, that is called a fundamental circuit. So you have to get a fundamental circuit. This is like the cord, and these are like the spanning tree edges. Together they will make a fundamental circuit. So we have to get a fundamental circuit. Now the question is how? So if you increase here, you can understand that you have to decrease this. So if you decrease this, then you have to increase this. If you increase this, then you have to decrease this. If you decrease this, then you have to increase this. And if you increase this, then you have to decrease this. So you can see that the closure is obtained. And this is shown. This is exactly what is shown here. All right, increase here, decrease here, increase here, decrease here, increase here, and decrease here. So you should note this closure. This closure is very important so that the table remain balanced. So what is the maximum that you can increase? You have to check that which one is the maximum that you can, minimum that you can decrease. Because you see, if you cannot decrease 8. If you decrease 8, I mean, sorry, not minimum, maximum that you can decrease. So if you think that you will decrease 8, then this 5 will become minus 3. That is not possible. So you have to check that which are going down, and out of that, which one is the minimum, that is the bottleneck. That means this 5 will go down and this 5 will go up here. This 5 will become 10, this 8 will become 3, this 4 will become 9, and this 15 will become 10. All right, so this is how the next table is obtained, and then we, this is how, this is exactly what is written. See how the closure is obtained. This is important. There should be non-basic entry cells, and all the rest should be basic variables. Maximum possible entry would be 5, because that is the maximum that reduced. So that is now reduced, and this 5 has moved here. So this is the new basic solution that we have got. So 6, 5, 10, 3, 9, and 10. So iteration 2 is obtained, and UV coefficients are computed again. Cij, Zij values are also computed for the non-basic cells. So if U2 equal to 0, then this should be 18. This is 14. This 14 will give this 4. This 4 will give this 37. This 37 will give this minus 24. And this minus 24 will give this 45. And then compute the Cj minus Zj. So 23 minus 0 minus 37 minus 14. 17 minus 0 minus 45 minus 28. And this one 32 minus 49 minus 17. All right, so any doubt up to this point? If you have any question, please ask. Okay, so I hope, because this is a repeat up to this point, so I'm sure in the last class you might have understood it well, and therefore, let us proceed quickly, because beyond this problem we have to discuss something more. All right, so therefore we see that that we have to make some entry here. Then the closure is obtained once again. This goes down, this goes up, this goes down, goes up, goes down. So again, the minimum, that the maximum that can go down, all the go down you have to check. So what goes down? The 6 goes down, 3 goes down, 10 goes down. That means the only 3 can be shifted. So this 3 is shifted now, and that is the at iteration 3. This is going to be our next table. Again, the UV coefficients are computed, and the Cij minus Zij values are obtained, and then we find the best possible square is F3W2. So you tell me which cells are going to form the closure. So if you make some entry at F3W2, F3W2, that is here, which one will go down? Which one will go down column wise? F2W2. So if F2W2 goes up, then which one will go down? Yes. And which one will then finally go down? That is F3W4. So which will balance the going up of F3W2. So you see, this is how the closure is obtained. All right. So the closure is obtained in this manner. All right, so this is exactly how the closure is obtained, and this closure is very important because that is going to decide the flows. Because see, look, all these quantities are the amount that will flow from F1 to W1, F1 to W4, etc. So this is really what is called flow balance. All right, so this is how exactly what you just now said. This goes up, this goes down, this goes up, this goes down, this goes up, and this goes down. Right, so when that is done, then we get the new iteration, that is the iteration 4. And after 4th iteration, this is how the values stand. So once again, we compute the U's and V's, and then Cij minus Zij, and see only one cell is now positive, and that cell is your F2W4. And F2W4, if you make some entry, which one should go down? Tell me which one will go down, F1W4 or F3W4? Yes, F3W4. Because if you take F1W4, you will find nothing else to increase. All right. So F3W4 is going to go down, and F3, this one will then go up, and this one will then go down. So that is going to be our new closure. And after getting that closure, then we get this solution. So that is F1W4 equal to 11, F2W1 equal to 6, F2W2 equal to 3, F2W4 equal to 4, F3W2 equal to 7, and F3W3 equal to 12. Again, the UV coefficients are computed, and then I find that Cij minus Zij values are all positive. This one is missed out, but nevertheless, this is also positive. 41 minus 9 minus 23. So this is also positive. All right. So iteration 5 is obtained, and UV coefficients are computed again. Cij minus Zij values are computed. All are plus. That means, no other cell is a profitable cell, and therefore this is the optimum solution. So what is the optimum solution? F1 will send to W4, F2 will send to W1, W2 and W4. F3 will send to W2 and W3. And the total cost comes to TC equal to 796. How it is obtained? 11 into 13, 4 into 23, 3 into 18, 6 into 17, 7 into 27, 12 into 18, and then sum total. All right. So all of you have understood that how the optimum solution is obtained by using the northwest corner rule. So only thing that we have to see that it took us as much as 5 iterations to get at the final solution. And if you really follow, then what has happened that we had a very big entry at this cell, which is the most unfavorable cell. It is not favorable at all. The cost is very high. But still we had 15 entry there because we followed a starting method, that is the northwest corner rule, to make an initial allocation, and that method is not efficient. So it actually tells us that an efficient method is really required right in the beginning so that we can get a good initial solution. So finding an initial basic feasible solution is an important thing, and we shall discuss 3 methods to find the initial basic solution for a balanced transportation problem. What are they? Northwest corner rule, minimum cost method, and Vogel's method. Out of these, we have already found that northwest corner rule is not an efficient method to find a good initial basic feasible solution for a balanced transportation problem. So we are not very happy with the northwest corner rule. But there is a reason why northwest corner rule has come. Anyhow, that I shall explain later. We shall discuss the other 2 methods, that is the minimum cost method and the Vogel's method, or sometimes called Vogel's approximation method, or VAM. In fact, there is another method which I am not discussing, that is called the Russell's approximation method, or RAM. Right? So there is a Vogel's method, there is also a Russell's method. But we are not going to discuss Russell's method because that is slightly complicated. But anyhow, the Vogel's method is good. And most of the time, we actually use what is known as the Vogel's method, or the VAM, to find a good initial basic feasible solution. All right, let us now see the minimum cost method. So in the minimum cost method, find the cell ij with the smallest unit transportation cost. Assign shipment as much as possible in this cell. How much to assign? It is the minimum of availability and the demand. Now cross out row I or column J as the case may be and reduce the corresponding availability and demand by the amount assigned. Now choose from the cells that are not crossed out another cell with the minimum transportation cost and repeat steps 1 and 2. Continue until m plus n minus 1 basic variables are obtained. So there could be a situation where we may not get m plus n minus 1 basic variables. The situation will be discussed later. So what are the steps? Steps that first of all, find a cell ij with the smallest unit transportation cost. That means we are assigning at the smallest possible cell. After the assigning and the usual things, we cross out the row or column which is filled, and the remaining cells again we find a minimum cost. All right, so like this is a simple method basically. So first of all, which one is the smallest cost here? Out of all the different costs, if you really look at, the smallest possible cell is F1W4 in terms of costs. Is it not? The cost is only 13 per unit. So this is the smallest cell and we try to make some entry there. So we see that the row wise total is 11, column wise total is 15. That means only an entry of 11 can be made there. So as we make an entry of 11, then we cross out the row because row is filled up, but column is not filled up, and 4 units are remaining. So this first step is very clear to all of you. Have you understood the first step? So now you tell me what should be the next cell where we should make some entry? And not W4, F2, W3, because that is the smallest cell. next smallest cell out of the remaining, is it not? So this is the minimum cost method. So F2W3 is going to be the next cell where we can make some entry. And now how much entry is possible? 12, because row column wise 12, row wise 13, so 12 entry is possible there. So this is exactly what is done, that F2W3 is the next smallest cell, so we make an entry of 12 in that particular cell. All right. So and then we cross out these 12 and these 13, only one is remaining. Now out of the remaining 6 cells, which one is the minimum? That is F2W1. So we should make some entry. How much entry is possible? 1, not 6, because this side only 1 is now available. So only one entry is possible there. So that one entry is made next. Just you see, this is exactly how it is proceeding. And now you see it has become trivial, because no point going any further, because now you don't have any choice, because only 3 cells are remaining and you have to fill up the remaining amount. So that means now you have to put this remaining amount 5 here, remaining amount 10 here, and remaining amount 4 here. Can you see that? Because you see only 3 cells are left and you have to balance everything. So no point continuing that, okay, 27 is minimum, let me put 10 there. So you can do like that also, but nevertheless, that is exactly what is going to happen. So we did that way only. We first put 10, and after putting 10, then we put the remaining 5 and 4, because now no other choice but fill up F3W1 with 5 and F3W4 with 4. So this is what we have got, and we have got an initial solution, which is 11, 1, 12, 5, 10, 4. Look, 3 plus 4 minus 1, that is 6 entries are there. So that is also satisfied. So this is our going to be our initial basic feasible solution. So this is our initial basic feasible solution with the uh, minimum possible cost, right? Minimum cost method. So you see the minimum cost method actually ends here. All right. So we don't have anything further to do with the minimum possible cost method. Now this is the first table that we have got obtained. Now we have to solve it by the transportation algorithm. So essentially the problem is solved in 2-3 steps. The first step is find an initial solution. There are 3 methods. So you see, suppose somebody asks you what are some methods to solve transportation problem. Then you should tell not those northwest corner rule, VAM, etc. They are not methods to solve transportation problem. Methods to solve transportation problem is that first you see that the problem is balanced or not. That is the first thing to see. So yes, is the problem balanced? Yes, problem is balanced. Then find a good initial basic feasible solution. That is step number 1. After finding a good initial basic feasible solution, which we have found now, then you compute the Cj minus Zj, or in this case Cij minus Zij values with the help of UV method. Right? The UVs are nothing but the dual variables which represents cost potentials. U's are directly and V's are in a negative sense. All right. So those dual variables will give U's and UI's and VJ's, and in fact UI plus VJ equal to Cij for basic variables, and for non-basic variables Cij minus UI minus VJ is equal to Cij minus Zij. So using that method, you find out which variable to enter, which variable to, leave. So, we find that after computing the UIs and VJs, this particular cell, that is F3W3, is giving the most negative value. So that means F3W3 is to enter. Now question is which one to leave? That is to be found out by finding the closure, and which is like obtaining a fundamental circuit with the spanning tree edges. These are can be called as spanning tree edges. So if we make some entry, then this goes down, this goes up, and this goes down. So out of that, the this goes up, this goes down, this goes up, this goes down, That means the 5 is the maximum that can go down. So that means this 5 will come here. This will become 7 and this will become 6. All right. So this is the method. All right. Then after that, again, you compute the Cij minus Zij values as you solve the linear programming problem. Same thing you are doing in a transportation algorithm. And finally, the solution is obtained. So that is how the transportation problems are solved. But then suppose someone asks you another question that look here, a good initial basic feasible solution is so important for transportation problem solution. So what are some methods to find a good initial basic feasible solution? At that time, you must tell that look, there are few methods. One is the northwest corner rule, which is not very efficient. There are minimum cost method, and there is Vogel's approximation method and also Russell's approximation method. So is it okay? So please understand, some of you might be thinking because I have given too much weight to the northwest corner rule in the previous problem, and you might be thinking that northwest corner rule is the rule to solve the transportation problem. Unfortunately, no. The northwest corner rule, minimum cost, or Vogel's approximation method, these are only methods to find out a good initial basic feasible solution. Is this point very clear to all of you? Good. So now that it is so, then again we compute the UIs and VJs and we find the Cij minus Zij values. Then we also find the closure. So the closure is coming like this. So there is some entry here, entry down here. And as I said earlier, the minimum amount is 5. So 5 would come here. So that is what has happened. The 5 has come here. Again, we compute the UIs and VJs. So if I have 0 here, then this will be 17. If I have 0 here, then this will be 14. And because this 14, so it should be 4. This 4, so it should be 37. This 37, so this should be minus 24. So all the UIs and VJs are obtained, and thereafter the Cij minus Zijs are obtained as well. So this one is 21 plus 24 minus 17, 16 plus 24 minus 23, 25 plus 24 minus 14, so all plus. This one is 18 minus 0 minus 23, so minus 5, 23 minus 0 minus 37 minus 14. This one is 32 minus 4 minus 17, so plus. So look here, F2W4 is now the most attractive cell, and therefore some entry can be made there. And how the closure is obtained? The closure will be obtained. This is very simple. This goes up, this goes down, this goes up, this goes down, right? And out of that, that is going down, 4 is the maximum and minimum. So obviously maximum entry that is possible to be here is 4. So that would do like this. So that is how the closure is obtained. And after we obtain the closure, we see that an entry of 4 can be made here. And therefore the entry that we got is 11, 6, 3, 4, 10 and 9. All right. So this is iteration 3 is obtained, but unfortunately even now we could not find a solution. So again we have to compute the UV coefficients. Let us say U2 equal to 0. So this should be 17, this should be 14, that should be 23. So a good idea is to put 0 to a cell where most of them can be obtained directly. So since this is 14 and this is 18, so this should be 4. Since this is 4 and this is 27, that should be 23. And then since this is 0 and this is 23, this is 23 and this is 13. So this should be minus 10. All right, so these are obtained, and thereafter we see only one is negative, that is this 18. So 18 minus 0 minus 23, so minus 5. So we make some entry. Now tell me which one should be go down, which one should go up, and what should be the entry now? So if you make some entry at F2W2, which one should go down? Yeah, W2. So F3W2 should go down, and therefore F3W3 should go up. And F3, F2, W3 should go down. So out of that is going down, which one is the bottleneck? F2, W3. So that means 3 would come here. All right. So then we bring 3 out there, and we see that this is going to be 3, this is going to be 7, this is going to be 12, and that will be blank. All right. So that is how we find the closure, and that closure would really obtain the new solution. All right, so that is what we put in that. So 3 is here, then 7 is here, and the 12 is here. All right, so now this is the optimum solution. So you see, it is optimum because again, if you put UIs and VJs, then you find that these solutions are put accordingly. Is it clear? So once again, we see that we have got the new optimum solution, and these new optimum solutions are going to be, in this range, and these are different Cij minus Zij values, and those Cij minus Jij values are going to be positive in that manner. Is it all right? So this is how we have got, but even then, if you really compare with the basic feasible solution that we got in the method 1, that is the northwest corner rule, which took 5 iterations, even with the minimum cost method, it took us as many as 4 iterations. Now can you tell me that since we are putting entries in the minimum possible cost, why it happened that we have to have so many iterations? What has really gone wrong so that we could not find the solution easily, and we had to require so many iterations before we could find the optimum solution? What is the reason for that? Is the question clear? What exactly I'm trying to get at? No, see, if you look at this, in the minimum cost method, the basic feasible solution initially that we obtained is this one. That is 11, 1, 12, 5, 10, and 4. Look here, although we are trying to enter initially to the least possible cost square, like 11, then 14, and then 17, but towards the end, we had to choose certain squares which are not very good. Is it not? We had to choose certain squares which are not very good. So basically, this is very interesting. Look here, this 23 is much better than this 41. Is it not? So if we make some entry here, we can reduce a lot of costs. But then we make some entry here, although it is very good. But suppose even as a compromise choice, if you would have made some entry here, it wouldn't have been that bad. Because you see, here you reduce 18, here you reduce 4, increase 4. So if you can reduce 18, you should be okay with increase of 4. So that basically says it is not exactly the minimum which is very important. It is the relative comparison of values which are actually more important. So that is why, what really happens if you keep entering at the minimum cost, initially they are quite okay. But at the end, because you have to have basic feasible solutions of required number, you end up entering values in squares which are not very good. So these perhaps can be avoided by a better method. So that is the difficulty with the minimum cost method. We got the optimum solution, yes, but look here, exactly that is what has happened in the optimum solution. We have made entry here and we made entry here. Although you see the 14 is the best possible square in this column, we are not making entry in 14. We are making entry in 18 if you look at this column. Why? Because when some row or column is to be seen, it is to be seen both sides. You see, uh, row wise, this is the best possible square, but column wise, it is not the best, right? So you have to see both row side as well as column side, and then by comparing both, we have to come up to a solution. So this is exactly what is exploited in the Vogel's approximation method. Let me tell you the steps. First of all, determine the minimum penalties for not utilizing the best possible cells for all the rows and all the columns. So we are talking about the minimum penalties. So what are some minimum penalties? You see, if we go these row wise, what is the minimum penalty? What is the best possible square? 13. What is the next best? 16. What is the next best? 21. So if you cannot use F1W4, what is the minimum penalty that you are going to give? 3. Because if you cannot utilize this square, then you should utilize this square, is it not? So that means the minimum penalty for not utilizing the best possible square or best possible cell is going to be 16 minus 13, that is equal to 3. That means you will pay a penalty of 3 if you cannot make an entry at F1W4. Instead, you make an entry at F1W2. So similarly, and this row, best square is 14, next best is 17. So penalty is 3. Here 18 and 27, so 9. This way 17 and 21, that is 4, 16 and 18, that is 2, 14 and 18, that is 4, and 13 and 23, that is 10. So these are the minimum penalties, 3, 3, 9, 4, 2, 4, 10. And we try to make some allocation in a square which is having the maximum of this minimum penalty is to be avoided. Because you see, suppose you cannot make an entry here, then you have to make entry here. What is the penalty you are paying? 10. This way, if you do not enter, so penalty is 3. This way the penalty is 9. So you see, it is always going to be good if you avoid incurring the maximum of this minimum penalty. So choose the maximum of this minimum penalty and go to that particular square and then make some entry. All right. So this is exactly what you are doing. Determine the minimum penalties for not utilizing the best possible cells for all the rows and all the columns, and then avoid incurring the maximum of these minimum penalties by allocating the maximum possible amount in a suitable cell. So after you made that entry, cross out the row I and column J as the case may be, and reduce the corresponding availability and demand by the amount assigned. Is it all right? So this is the usual method which is there, and repeat the above steps till m plus n minus 1 basic variables are obtained. Again the same, there could be a situation where we may not get m plus n minus 1 basic variables. This situation will be discussed later. So what happens in Vogel's approximation method? We find the minimum penalties, and after finding the minimum penalties, we find out the maximum of these minimum penalties and make some entry so that these maximum of these minimum penalties are avoided. Is all right? So where do we make some entry? We make entry at this square, because out of all these minimum penalties, the maximum is 10. So we try to avoid this maximum of these minimum penalties and make some entry in the corresponding square. So we make an entry of 11 out there. All right. So we make an 11 entry out there. So as you then see both row wise and column wise, in the row wise, then the row is satisfied. But in the column wise, the column is not satisfied because total is 15. So 4 is remaining. So we do not cross out the column, but we cross out the row. the row is then crossed out. These 11 is also gone. So again is repeated for the remaining squares. So you see this 3 penalty has lost its meaning, is it not? So this 3 is actually crossed out. All right, now out of the remaining, can you now tell me how much should be the row wise penalties, these the row wise, and how much should be the column wise penalty? First you talk about row wise. Will these row wise penalties change? Row wise penalties will not change because we have not made any differences in those squares, right? Since we have made no differences in these squares, the row wise penalties will remain exactly same. Is it all right? Now, however, the column wise penalties are going to change. So what will happen? That these 17 and these 32, so the gap is 15. So this is the best square, this is the next best square, this is gone. So that means this 4 will now become 15. How much this will become? This will become 9. This will become 4. This will remain 4. And this will become 18. So all of you can see that what are going to be our new penalties, that is the minimum penalties. Minimum penalties for not utilizing the best possible squares. Is it clear to all of you, or is there somebody who thinks that you need a little bit more explanation? If there is a tie. Okay,
Yes, sir.
that's a very good question. If there is a tie, the answer is very simple, that break the tie arbitrarily. All right. However, if you break the tie arbitrarily, it is possible that you might get a different initial basic feasible solution than others who have broken the tie in a different manner. See, our purpose is basically to find a good basic initial feasible solution. As long as we get it, we are happy. Is it not? And there could be some variations. So when there is a tie, we have to arbitrarily break the tie. You can make some mental rule that we shall take the row. Although there is no such thing, you could have taken the column also. But to make uniformity so that everyone gets the same answer, you can think that we shall break the tie in this manner, that if there is a tie between row and the column, then we shall take the row. But that if there is a tie between two rows, obviously you have to take one of them. Again, you might think of, okay, let me take the leftmost row or something like that. Anyhow, so these are going to be our new penalty values. This 3 is crossed out because this row is utilized. So these 3 remains, this 9 remains, this 4 has now become 15, this 2 has now become 9, this 4 has remained, this 10 has become 18. So 10 is going to be our new square, and how much should we enter there? The rule is very simple. Maximum of these minimum penalties should be avoided. What is the maximum of these minimum penalties now? Right. So 18 is the maximum of these minimum penalties. So we should avoid incurring the maximum of these minimum penalties. And that means, how can this be avoided? By going through this column, finding the best possible square and make some entry there. So if this is that square, and row wise total is 4 only, and column wise also, you see, if I make some entry, the column wise total is 13. Row wise column is 13 and column wise total is 4. That means only an entry of 4 can be made out here. Is it all right? So if you agree, then exactly that is what is done. An entry of 4 has been made in this particular square. So now this column is also satisfied, and this row wise total is reduced by 4. So now this has become 9, and these are already gone, and this is also gone. So they are all crossed out. So because then a change is in the row, so there won't be any change in the columns, right? So there won't be any change in the column. So this remains 15, minimum penalty. The minimum penalty, this remains 9, and minimum penalty here becomes 4. So this side, the minimum penalty now become 14 and 17, 3. And here also it becomes 18 and 27, so 9. So now exactly the question that one of you asked a few minutes back, that if there is a tie in the minimum penalties, maximum of these minimum penalties, then which one should I choose? So exactly you see that after the minimum penalties are recalculated, there is a tie. This particular column, that the max minimum penalty is 9, and this particular column minimum penalty is again 9. So there is a tie. Now question is which one? You can choose the row or the column, any one of that. So what we have done, we have chosen, I think, these are the minimum penalties. They are recalculated. So then, we have chosen, sorry, which one should we choose? No, I think there is no, I'm sorry for it. There is no, there's minimum penalties. There are no, this is not a tie because 15 was minimum, is it not? The minimum is 15, not 9, right? So go back
Yes, sir.
there and please check. The minimum is 15 and not 9. So since 15 is minimum, it's very obvious this column has to be chosen, and we have to make some entry 17 there. So this side total is 6 and this side total is 9. So a entry of 6 can be made here. All right, so entry of 6 is made, and after making this entry of 6, this column is satisfied, and along this row we see and remaining 3 units are still remaining. Is it all right? So this is our next, and after that again the penalties are recomputed, and now we have the tie. All right, because this side the again when it has recomputed, this 3 has become 4. This becomes 9, this becomes 9, and this becomes 4. All right, so we have to break the tie in an arbitrary manner. So either you can take the row or you can take the column. So it is your choice, so whether you want to make entry here or you want to make entry here, because both are competitive squares. Sorry, because this side is 9, so this side is also 9. So if this is 9, then the best possible square is this, and if you take this 9, then the best possible square is this. So you have to choose between these two squares. So I think we have chosen these, column wise. So, and then we have put 3 here. All right, so we put 3. Now, moment we put an entry of 3 here, then this particular row is satisfied. Now, obviously, can you see that now it has become trivial and we cannot make any further entry in this particular, there is no point in doing any calculation because only one squares are left, and only this 9 is to be there. So that means we have to make some entry here, and then we also have to make some entry here because at this point further calculation has no meaning. All right, so these minimum computations are ceased to be there, and now we have got the basic feasible solution from the Vogel's approximation method. So that has been obtained and this part of the job is done. All right, so Vogel's approximation is completed, and the solution we have got is F1W4 is 11, F2W1 is 6, F2W2 is 3, F2W4 is 4, and F3W2 is 7, and F3W3 is 12. So we have already got the basic feasible solution from the Vogel's approximation method. Now, this is going to be our initial basic feasible solution, and we have to now start the actual transportation algorithm. So what we do, we call the iteration 1, and again we computed the UV coefficients. So how the UV coefficients are computed? If we put a 0 here, then we get a 17 here, we get an 18 here, we get a 23 here. Because this 23 and this 13, we got a minus 10 here, and because of these 18 we get a 9 here, and because of these 9 we get a 9 here. As a cross check, always please do not forget to do a cross check. That cross check is also very important. Minus 10 plus 23 equal to 13. 0 plus 17 equal to 17. 0 plus 18 equal to 18. 0 plus 23 equal to 23. 9 plus 18 equal to 27. 9 plus 9 equal to 18. So all are done, and then the Cij minus Zij values are obtained, and incidentally now we find all of them as positive, because 21 plus 10 minus of minus 10 minus 17 plus 16 minus of minus 10 plus 25 minus of minus 10 minus 9 plus 14 minus 0 minus 9 plus 32 minus 9 minus 17 plus 41 minus 9 minus 23 plus. So all of them are plus, and now the iteration 1 is obtained. UV coefficients are now computed. Cij minus Zij values are also computed for the non-basic cells, and the optimum table is now obtained in the first iteration only. So you see, this is the a good thing about that Vogel's approximation method, and we could get the optimum solution in the first iteration itself. So a question automatically, does the Vogel's approximation method guarantees an optimal solution? What is your comment on that? That's a very good answer, that no. Answer is definitely no. The Vogel's approximation method is only giving us an initial basic feasible solution to begin with the problem. Incidentally, it has become optimal in this particular case. Now the question is, will it be optimal in all situations? Answer is no. There will be many situations we shall find where the Vogel's approximation solution method will give us a good initial solution to begin with. We might have to have less number of iterations, but definitely not the optimum solution all the time. All right, but sometimes yes, it will give the optimum solution at the first go. So therefore, the method that we are going to follow to solve transportation problems, the first we have to compute, or we have to obtain a good basic initial feasible solution by using a good starting method such as Vogel's approximation method. The minimum cost method also has its problem, like the northwest corner rule. And after finding a good basic initial feasible solution, and thereafter we have to use the UV method to compute the Cij minus Jij values. And if we get some minus somewhere, then we have to make some entry there, obtain the closure, that is the flow balance, and after getting the closure, increase or decrease, and so that the entering variable and the leaving variables are decided. Is it clear? So this is exactly how the iterations are obtained, and how basic feasible solutions and thereafter the optimum solutions are obtained by the transportation algorithm. Is it clear? Any question on the Vogel's approximation method? So
Okay.
I stop the recording now.